So when we last left off, we focused on drawing unique stereoisomers and making sure to identify meso compounds. So let's look at the following example. And let's try to draw all stereoisomers for the following compound and label any meso compounds that are present. Remember, meso compounds, compounds with an axis of symmetry, are achiral, and sets of meso compounds are considered identical compounds. So, I'd like everyone to start off today's session to take about 4 to 5 minutes and focus on drawing out the unique stereoisomers for the following molecule. Remember your first order of business. So the first order of business is to label our stereocenters. And each of these stereocenters, we're going to then draw the different permutations of stereoisomers that vary at each of these two stereocenters. So I'd like everyone to take a moment and to try to share their proposed structures using the annotate tool. I'd like you to try and draw out as a class each set of stereoisomers for this compound and then identify any meso compounds that are in your set. And remember, meso compounds have an axis of symmetry and are identical. So let's get started with this example. Just as a reminder, you can use the annotate tool under the meeting features tab in your Zoom view. So let's take about 4 to 5 minutes and let's try to draw the different stereoisomers for the following compound. You can also take a photo of your work and send it as a message in the chat, and I'd be happy to provide feedback. So let's work together as a class on contributing the different stereoisomers for the following compound, and let's try to draw them out using the annotate tool on the class whiteboard. So let's try to get some shared responses on the class whiteboard using the annotate feature for each of the different stereoisomers of the following compound. And remember, multiple students can annotate on the whiteboard at once, so don't be shy to share your responses on the whiteboard to add to this class discussion. So we have our first set of compounds drawn. And let's analyze each of these compounds now, and let's try to think, are any of these compounds symmetrical? Are any of these compounds meso? Perfect, exactly right. This second compound is meso because it possesses a clear axis of symmetry. Now, we're not quite done because we would expect 2 to the n stereoisomers, and 2 to the second would give us an expected number of 4 stereoisomers, assuming no meso compounds. So we still have 2 more structures to draw. So let's keep working on this example and let's try to draw out another set of structures. So we have part of our second set of stereoisomers drawn. Is there one more potential structure that we can draw just for completeness? I do notice that you're alluding to the fact that meso compounds are identical. Would you be able to draw the other quote unquote stereoisomer, even though it's not a genuine stereoisomer because it's meso? Perfect. So again, for this compound, we have a set of meso compounds, and these two meso compounds are identical. We have a set of enantiomers. As we can see, these two compounds are enantiomers, as they have the opposite configuration and opposite stereochemistry at each of our chiral centers. So just to make sure that the response is saved, I'm going to clear these drawings. This is perfect for this problem. We've identified all the stereoisomers, identified two of our compounds as meso or identical. So for this compound, we only have 3 unique stereoisomers and only 2 chiral species. So let's draw out our solution. Let's draw out and rewrite the student solution as this was phrased perfectly. So our first compound looks something like this. As we notice, there's an axis of symmetry, so this compound is meso. It's achiral. Likewise, the quote-unquote enantiomer, it's not a genuine enantiomer because it's meso, looks something like this. Both of these compounds are meso, so both of these compounds are identical. We can look at an alternative stereochemistry, and that gives us the following structure. And looking at the enantiomer of this compound with the exact opposite configuration at each chiral center, that gives us another potential stereoisomer. These two compounds are enantiomers because they have the opposite configuration at each of our chiral centers. Does that make sense to everyone? Does this problem make sense? So the key trick in this problem is making sure, one, you note your total number of possible stereoisomers, and then you make sure to exclude your meso compounds. Any other questions on this example? If not, let's keep going now. And let's talk a little bit about Fischer projections. So Fischer projections are another way of drawing out compounds with multiple chiral centers. This primarily pops up when you're dealing with sugars. So a Fischer projection is a 2D drawing of a molecule that shows a chiral carbon at the intersection of 2 lines. Now, when we think about a Fischer projection, the horizontal lines represent bonds that project out of the plane of the screen. So the horizontal lines can be considered wedges, while the vertical lines represent bonds that project into the plane of the screen. You can think of them as the dashes. So it's common in Fischer projections that the most oxidized carbon, which for sugars is almost overwhelmingly going to be the aldehyde or ketone group, is represented at the top of our structure. Okay, so now that we have that established, let's talk a little bit about how we analyze Fischer projections. So, when you draw a Fischer projection, as we see from this handy photo next to it, the horizontal groups are pointing out towards us. So both of these horizontal groups are pointing out towards us, while the vertical line groups are pointing away from us, and they're pointing into the page. Now we can take these Fischer projections and we can convert them to our traditional Dash Wedge notation. And to do that, we're really going to need to make some models of these structures. So suppose that we are given the following Fischer projection. The first order of business is to convert this Fischer projection into Dash Wedge notation. Each of our horizontal lines get a wedge, each of our vertical lines get a dash. So now that we have that established, let's make a model of this structure. Let's break out our model kits and let's make a model of this structure. Just like before, we're trying to visualize how to rotate. We're trying to visualize bond rotation in order to most accurately portray this Fischer projection structure using Dash Wedge notation. It's also invaluable at assisting us in assigning the stereochemistry given a Fischer projection. So there are many different ways to draw organic molecules, and it's important that we're familiar with these different depictions of organic molecules because different subfields will often utilize different ways of drawing and depicting organic molecules. Okay, so let's now turn on the camera and let's share our model. Here we go. Okay, so here is our model of the following structure. First, does everyone notice how the hydrogen and hydroxyl group are pointing out of the page? Does everyone see how the hydrogen and hydroxyl group are pointing out of the page? Does everyone see that? And does everyone see that our alcohol and our methylene group with the alcohol and that our aldehyde are pointing away from us? Does everyone see how these two groups are pointing away from us? So this directly maps on to our dash wedge depiction of the Fischer projection. So what we're going to do now, just like always, is we're going to rotate our molecule so the hydrogen is in the back. We're going to rotate our molecule so the hydrogen is in the back. Okay, now that we've rotated our molecule so the hydrogen is in the back, we're just going to draw what we see. So in this case, we're going to draw our alcohol pointing up, our aldehyde on the right, and our methylene group with our alcohol on the left. So now that we have this established, we can assign priority just like normal. The alcohol's the alcohol is priority 1, the aldehyde is priority 2, and the methylene group is priority 3. Tracing from highest to lowest priority, we'd assign this stereocenter as R. Does that make sense to everyone? Does that process make sense? So let's apply what we've learned here. Let's try to apply what we've learned, and let's tackle an example to apply our knowledge. So I'd like you to take a look at the following compound, and I'd like you to indicate the configuration of each stereocenter in the following compound. So I'd like you to indicate the stereochemistry and assign the configuration of our single stereocenter in this molecule. You'll definitely need to make a model kit, and you're more than welcome to share your proposed redrawn structure using the annotate tool. I'd like to see from everyone a proposed stereochemical assignment as RS for the following stereocenter in this molecule. And we'll discuss this example in about 3 minutes. And if you have any questions, don't be shy to ask them verbally or in the chat. So let's try to get a few assigned stereochemistries in the chat. And if possible, if students can share using the annotate feature, their redrawn structure to help us understand their logic in assigning the stereochemistry, that would be great. Otherwise, if you have any questions, don't be shy to ask your questions verbally or in the chat. And we'll discuss in about 2 minutes. And if you have any questions working through this example, or if there's a part of this problem that you're stuck on, don't be shy to let me know in the chat, either using the public chat or the private Zoom chat, and I'd be happy to provide feedback and some direction in solving this problem. I'd like to see some students share the stereochemical assignment in the chat for this problem, or ask some questions before we discuss. What does everyone think for the stereochemistry of this stereocenter? Does anyone have a proposed assignment that they'd like to share, just so I can understand and get a sense of how how everyone is approaching this problem. So we have a proposed assignment of S. Do we have any other proposed assignments? Don't necessarily be shy to contradict your classmates. The more responses we have, the more I can understand how students are approaching these problems and provide more directed feedback. Does anyone else have a proposed assignment? Or does anyone else have a question on this example? So let's look at this example. So first and foremost, remember from Fischer projections, all of our horizontal lines are drawn as wedges and all of our vertical lines are drawn as dashes. Okay, so from that we have enough information now to put together a model of our structure. Again, if you're ever unsure, you can just put together a model kit and put together a model of your structure, and that will provide you a relatively unambiguous depiction and source to analyze and assess the stereochemistry of your molecule. And it makes it really easy to rotate your molecule into the correct overall arrangement. Okay. One moment, just adjusting my model kit. Okay, so here is our structure. Here is our structure. So as we notice, the alcohol and hydrogen are pointing out towards us, while our methylene group containing our other alcohol is pointing away from us. Our ethyl group is also pointing away from us. So now we want the hydrogen in the back. So what we're going to do is we're going to rotate this molecule so the hydrogen is in the back. And now what we're going to do is we're just going to draw what we see. So our alcohol's on the right, our methylene group's up top, our ethyl group's on the left, and our hydrogen's in the back. Assigning priority, oxygen is priority 1, the methylene group is priority 2, the ethyl group is priority 3. Going from highest to lowest priority, we see that this stereocenter would be assigned as S because we're going counterclockwise. Does that example make sense? Does this logic make sense to everyone? It's very similar to our previous examples on assigning stereochemistry. Any questions on this example? Any questions on this example that I can address? Okay, so let's keep going now. Fischer projections are really useful because they can readily show if two compounds are enantiomers or diastereo isomers. Essentially, the location of the substituent, left or right, relative to the backbone, determines the stereochemistry of that chiral center. It doesn't explicitly match R or S because depending on your top and bottom substituents, you'll have different priorities. But if two compounds have a substituent at a different position on a chiral center in a Fischer projection, the stereocenter has the opposite configuration. Diastereo isomers, as we've discussed, have different configurations at one or more, but not all of the chiral centers. So as we notice, if we look at both of these structures, we have a different configuration at one or more, but not all of our chiral centers. So this pair of Fischer projections, this pair of compounds represented by these Fischer projections would be diastereomers. Now, just to satisfy any academic curiosity that students may have, it's important to note that we also have a pair of enantiomers among these structures. Because as we notice, these two structures have the opposite configuration at both of our chiral centers. Does this idea make sense? So Fischer projections are really useful for quickly identifying diastereomers and enantiomers because the position of the substituents on the left or right-hand side directly impacts and directly determines the stereochemistry of our chiral centers. Does that make sense to everyone? Can I get some feedback in the chat that everyone's comfortable with this idea? You'll see this a lot when we talk about sugars. So, just to help everyone see what's going on here, let's take a look and let's analyze these structures and let's show that these two structures are in fact diastereo isomers. This is a very important instructive example. It's always important when you're presented with an idea or a proposal that you analyze that proposal to make sure that it's logical, that there are no major issues with how that proposal is presented. Okay, so let's make a model of our structure. And give me one moment to put together a model kit. I'd like you to follow along and make a model of this top structure. So that way we can analyze and assign the stereochemistry at each chiral center in this molecule. So let's take a moment and let's put together a model. Note, a lot of these structures have been very carefully chosen to avoid accidentally giving a meso compound. This compound's not meso, it's one carbon away from being meso though, just as a side note. Okay, so I've made a model of this first structure. So it looks something like this. So does everyone see that our two bromines in purple are on the right-hand side? Does everyone see? Okay, perfect. The hydrogens are on the left, and both of these substituents that are horizontal are pointing out of the plane of the page. Our ethyl group is pointing back, and our methyl group is pointing back. Now that we have this structure, what we're going to do is we're going to rotate this molecule so the hydrogens are in the back. So the easiest way to go about doing that, quite simply, is just to rotate our molecule 90 degrees. Now, all we have to do is draw what we see. So after rotation 90 degrees, both of our hydrogens are in the back, and we're just going to draw what we see now. So we have both of our bromines in front. I have my methyl group up top, and I have my ethyl group up top. Does everyone see that? Does everyone see that after rotation? So we started off with the following Fischer projection. And all we did was rotate the structure. 90 degrees. Does that make sense? We drew what we see, and we ended up with the following depiction of our molecule. Now that we have the following depiction shown here and here, we can assign the stereochemistry using our priority analysis. Bromine is priority 1, this alkyl bromide is priority 2, the ethyl is priority 3. So tracing this first center would be S. For our right-hand side, bromine is priority 1. The alkyl bromide's priority 2. The methyl is priority 3. So tracing, we have an R configuration. Does that make sense to everyone? Does that make sense to everyone? Now I want to note that for Fischer projections, the position of a substituent is correlated with a given stereochemistry, but it depends on the structure. So in this case, for this structure, we have an assignment of S and R. If we were looking at an entirely different Fischer projection, the substituent on the right may lead to an R stereochemistry. So it's important that you go through and manually assign the stereochemistry for at least one of your stereoisomers for Fischer projections. Can I get some confirmation that everyone understands the process that we use to assign the stereochemistry for this first molecule, for this first Fischer projection? Does that make sense to everyone? Okay, perfect. Now, the beautiful thing about Fischer projections is that they are very good at describing molecules after you change the configuration of a stereocenter, after you try and draw a diastereo isomer. So in this case, we move our bromine from the right to the left-hand side. If we change the position of our substituent, the stereochemistry will change. So what would our tentative assignment be for this structure? What would our tentative assignment be? This top stereocenter, instead of being S, would be R. Yep, exactly. What about this bottom stereocenter? From our previous experience, what do we know about this bottom center? It's still going to be R. Exactly. But you don't really have to take my word for it. There's no reason why we can't just test this. So I'm going to make a model and we'll be able to prove this to ourselves. Okay, so here is our revised model. So as we notice, this time the top bromine is on the left. So now what we're going to do is we're going to rotate this molecule so our hydrogens are in the back. So I rotated it first so both of my hydrogens are on the same side. And then I'm going to tilt my molecule so the hydrogens are in the back. Now all I have to do is draw what I see. And of course, your depiction of the molecule may be a little bit different. That's okay. There are many ways to rotate a molecule and get the same overall response. Okay. So first and foremost, I see I have both my hydrogens in the back. On the left-hand side, I have my ethyl group and my bromines up top. On the right-hand side, I have my methyl group up top and my bromine on the right. Does everyone see how I drew out this structure? Does everyone understand how I drew out this structure? Does everyone see how the model matches the structure that I've drawn? Can I get some confirmation? Perfect. So now that we have this structure drawn, we're all set to assign stereochemistry. So bromines priority 1, alkyl bromides priority 2, ethyls priority 3. So this center after modification is R. This second center, just to be sure, assigning our priority. Let me do that in a different color to make it easier for you to see. So for our second center, which theoretically shouldn't be changed, it is also R. So as we can see, if we change the position of our substituent from the right-hand side to the left-hand side, our stereochemistry flips. So this is the beauty of Fischer projections. They're very good at helping you notice diastereo isomers. Does that make sense to everyone? Does this example where we analyze some Fischer projections make sense? I always try to include things that are relevant when you're moving on to biology. And we'll see this again in 113, by the way, when we start to talk about hemiacetal formation and cyclization of sugars. Okay, so let's take a look at the following molecule. I'd like you to assign the configuration at each chiral center and tell me if the following compounds are enantiomers or diastereo isomers. Now, one thing that would be important to consider is that if you assign the stereochemistry for one molecule, you can use our Fischer projection shortcut to assign the stereochemistry for our second molecule. So I'd like us to focus on, I'm going to label these molecules A and B, and I'd like you to tell me the stereochemistry at each chiral center for A and B, and I'd like you to tell me whether these molecules are enantiomers or diastereo isomers. So let's take about 4 minutes to work on this example. And we'll discuss this example in about 4 minutes. And if you have any questions, don't be shy to ask them in the chat or verbally. And I'd like to see your proposed stereochemical assignments either drawn out onto the class whiteboard using the annotate feature, shared as a message in the chat, or shared verbally. And I'd be happy to provide feedback. I would also encourage you for these structures, it may be useful to share your 3D model depiction. And to do that, you can draw out your three-dimensional depiction of this Fischer projection. So that way we can discuss it and potentially note if the structure was drawn correctly after converting it into a dash wedge structure. So let's work on this example, and then we'll come together as a group to discuss in about 4 minutes. So don't be shy to share your stereochemical assignments. We have one student that's drawing out a three-dimensional dash wedge structure. That's great to see. So one way to help you visualize the dash wedge structures is you're essentially looking at the molecule from the side opposite to the hydrogens. Or you can think of it as turning the molecule on its side. So we have our proposed assignments of S and R in structure A. What does the class think? Does everyone agree with those assignments? Does this logic make sense? Does the three-dimensional picture drawn make sense to everyone? What does everyone think? I really want to try to draw out some input from other members of the class. Is everyone reaching similar conclusions? Do you have a different proposal to share? Really don't be shy to throw your perspective into these discussions. It's really important because it helps me as an instructor potentially highlight points that students may be unsure about or emphasize points that students are addressing in a very efficient and or interesting way. What does everyone think? Do these assignments make sense? To flesh out this discussion, I'd like to see, so if we have these assignments for A, what about B? What about B? So can I get some responses in the chat for structure B? We don't necessarily have to draw the 3D drawing for structure B. It's great though that a student is contributing it, and it would be good to see that as well to help make this point clear. But remember how when we discussed Fischer projections, if we change the position of our substituents, the stereochemistry of each center will change. So then, if we start with the S and R configuration when both of our substituents are on the right, when the substituents move to the left, we get in turn an R and S configuration. Exactly right, exactly right. Wonderful. So this is a nice, fully fleshed out discussion for this example. So let's clear these drawings And let's talk a little bit about each of these structures in detail. Let's talk a little bit about each of these structures in detail. I'm going to make a model kit, and I know it seems repetitive. We're always making a model kit. Well, while you're developing the basic skill to visualize molecules, it's always best to have a tool that helps you organize your thoughts. Eventually, you'll be able to move away from a model kit, but especially when you're first taking a class, there's no reason not to utilize every tool that you've been given at your disposal. And the more you practice using a tool, the more efficiently you can use that tool. Okay, so here is our initial structure. Here is our initial structure, right? We have our chlorine and alcohol on the right-hand side. We're going to rotate this molecule so our hydrogens are in the back. We're going to rotate this molecule so our hydrogens are in the back. And then now we're going to draw what we see. So we started off with the following structure. And after rotation, after rotating our molecule, we end up with the following. So drawing what we see, we have our methyl group followed by, oops, sorry, wrong direction. So we have our methyl group followed by our alcohol with our hydrogen in the back. We have our methyl group and our chlorine with our hydrogen in the back. It's almost as if we looked at the molecule from the side opposite to our hydrogens. That's another way of thinking about this. Okay, so now that we have this established, we can assign priority and verify the stereochemistry at each of our stereocenters. So priority 1, 2, and 3. So our alcohol stereocenter would be R. Priority next, looking at our stereocenter involving the chlorine, priority 1, 2, 3. The chlorine stereocenter would be S. Perfect. So the class handled this example wonderfully. Now, I'm going to utilize a shortcut now. If we change the position of our substituents in a Fischer projection, the stereochemistry will also change. What do we call two structures that have the exact opposite configuration at each stereocenter? What do we call compounds that are non-superimposable mirror images? They would be known as enantiomers. Exactly right. Exactly right. And the really nice thing about Fischer projections is you can see this quite clearly, right? You can draw almost a straightforward mirror plane and see that these two molecules are mirror images. Can I get some confirmation that everyone sees that these compounds are clearly mirror images of each other? Perfect. Any other questions on this example? When you take biochemistry, this may be important when you get to the chapter on sugars. So stereochemistry isn't going away by any stretch. Okay, so let's talk a little bit about chirality at other centers. So chirality at nitrogen, phosphorus, and sulfur. Now, nitrogen, there's a bit of an issue. Nitrogen can readily invert at room temperature. So nitrogen does not form a chiral center at room temperature, and we can't isolate individual enantiomers. Nitrogen undergoes rapid inversion at room temperature. What's really interesting is that phosphorus inverts more slowly. So chirality at phosphorus can be observed. You also see some temperature dependence where phosphorus can undergo inversion at higher temperatures. This is partially why many ligands, many chiral additives that are used in order to influence the stereochemical outcome of a reaction and create a chiral environment around a catalyst often are based on phosphorus-based ligands. So when you think about assigning stereochemistry for phosphorus, the lone pair is considered the lowest priority group for assignment. So in this case, looking at the following structure, the benzyl group or aryl group, or this benzene ring would be priority 1. The ethyl group would be priority 2. The methyl group would be priority 3, and the lone pair would be priority 4. So we can visualize this molecule after rotation as something like this. Going from highest to lowest priority, 1, 2, and 3, we see that we have an R configuration. Does this make sense to everyone? It's a nice little curiosity to consider. When you get to higher level organic classes, you'll see a lot more ligands, which are used to influence how the outcome of chemical reactions and the stereochemistry of the products observed in chemical reactions. And many of these ligands are phosphorus based. So it's useful to be able to assign the stereochemistry for phosphorus chiral centers. Okay, let's talk next about a very intriguing idea, and that concerns generation of chiral centers from chemical reactions, otherwise known as pro-chirality. Pro meaning essentially a center that can become a chiral center. So a pro-chirality describes a molecule that is achiral but can become chiral by a single alteration. So for example, addition of hydrogen to an asymmetrical ketone results in a chiral compound, right? Does everyone see how we're making a chiral center? Does everyone see how this product has a chiral center? So we designate a center a pro-chirality center if one or more substituents are modified. If when you modify one or more substituents, you generate a chiral center. So a pro-chirality center is defined as a center that can become chiral if one or more, or more correctly, if one substituent is modified via a chemical reaction. Okay, this primarily comes up when we talk about planar carbons, but it can also be observed for other functionalization reactions. So when we think about pro-chiral distinctions, it's best to think about molecules in terms of two faces, two sides of your molecule. So an sp3 carbon with two groups that are the same is a pro-chirality center. The identical groups are distinguished by arbitrarily assigning one of our groups, such as hydrogen, as higher priority than the other. If the center becomes R when that group or hydrogen is designated as higher priority, that substituent would be pro-R. If that stereo center becomes S, if that hydrogen is designated as higher priority, then that hydrogen would be pro-S. So let's show what I mean. Let's show what I mean by this. So let's pretend for a moment we have two hydrogens, right? Let's take a look at this pro-R hydrogen. So this hydrogen is considered pro-R. Why is that? We are going to arbitrarily designate our priority where the pro-R hydrogen is higher than our other hydrogen. That's why I'm putting it as priority 3. Does that make sense? So if your group is Pro-R, you're arbitrarily designating one of your groups as higher priority, and as a consequence of this priority assignment, when we look at the stereochemistry, our stereo center would be assigned as R, right? Does everyone see how if we assign that Pro-R hydrogen as higher priority, we have an R stereochemical assignment? So a Pro-R hydrogen would lead to an R stereocenter upon modification or substitution. Does that idea make sense? So the way that I like to think about it is I like to replace my hydrogen with a group X, and then I assign my stereochemistry for that center. If the stereochemistry is R, then that corresponding hydrogen would be Pro-R.
How do you know which hydrogen?
Now, if you know which hydrogen is Pro-R, the other hydrogen by definition must be Pro-S. But we can be a little more explicit with this. So let's look at our Pro-S hydrogen. So we're going to arbitrarily designate this Pro-S hydrogen as higher priority than our other hydrogen. Okay. Now, looking at the following structure, if we rotate our molecule, we end up with the following depiction. Now, when we assign the priority to each of our groups, we see that this center would be S. Ergo, this hydrogen is Pro-S. Does that make sense? Does that idea make sense to everyone? Can I get some feedback in the chat? Okay, so let's keep going with this idea. When you talk about planar molecules, planar faces or planar molecules that can become tetrahedral are different depending on whether they're approached from the top or the bottom face. So a center at the planar face at a carbon atom is designated as Re if the 3 groups in priority sequence are clockwise. So just to make a little key for us to remember, the Re designation occurs if your groups are clockwise in order of priority. Let's show what I mean by that. So from the Re approach, from the top down approach, going from highest to lowest priority, we see that we are clockwise. You can almost think of it like R, right? Does everyone see from the top approach the groups are clockwise? Now from the psi approach, it's important to consider that when we're looking at our molecule from the bottom up, now let me draw this structure. Let me make a model of this structure because it's often hard to see what changes when we look at the Re and psi face. The psi designation occurs if when you approach the molecule from that face, your groups are counterclockwise in order of priority. Now, what often trips students up a little bit, what often gives students a little bit of trouble in this example is that when you approach from the opposite face, you have a different view of your molecule. So let me put together a model of the following structure. And I would encourage you to make your own model as well as I'm putting together this model kit. Okay, we're almost finished putting together this structure. And it's really important to be as deliberate as possible with how you set up and how you start to view your molecules from different three-dimensional perspectives. So that way you can avoid making relatively straightforward mistakes that would cost you a small number of points on the exam. So it's really important to be as deliberate as possible. Make sure you're double checking your structures. Okay, so here is our three-dimensional view of the following molecule. So let's pretend for a moment that we are attacking from the re face. So we're attacking, and if we look at the ordering of our substituents, if we order our groups in terms of priority, if we're attacking from the perspective of the re face, we are going clockwise from highest to lowest priority. Now, if you're approaching from the psi face, you're approaching from the opposite face of our molecule. So let's draw this opposite approach. So if we're viewing our approach from the psi face, when we think about our substituents and we order them from lowest to highest priority, we see we're going counterclockwise. So it's almost like a quote unquote S designation. Does everyone see how the two faces that we're approaching from are different? Here is the re face. Here is the psi face. Does everyone see how the relative arrangement of substituents is different? Perfect. Any questions on that idea? So to help us visualize that, if we think about our approaches, if we're approaching from, in this case, we're showcasing the approach from the re face. That in turn, upon addition of our group X, leads to a stereo center with the opposite configuration as the approach from the psi face. Does this example of pro-chiral faces make sense to everyone? Addition, depending on whether attacking from the re or psi face, leads to two different products. From the re face, our groups in order from highest to lowest priority are clockwise. From the psi face, our groups from the highest to lowest priority are counterclockwise. Any questions on that idea? Any questions on that idea? Okay, let's keep going then. And let's talk briefly about this idea of how do we separate enantiomers. Well, there's a bit of an issue with enantiomers in that enantiomers have identical physical properties, so they cannot be easily separated. However, there's a trick to this. Diastereo isomers have different physical properties and can be separated via physical separations. Thus, one common trick to separate enantiomers is you can use a chiral resolving agent to convert our enantiomer into a set of diastereomeric salts. So, comparing, for example, the R and S enantiomers, if we have a pair of enantiomers, they're going to be very difficult to separate, if not impossible, via physical means. So, if we treat it with a chiral resolving agent, now we have a set of diastereomers which we can separate using physical methods. These diastereomers can be separated by their differing solubility, and then the resolving agent can be removed. So this is practically how often enantiomers can be resolved or separated. Resolution, in my opinion, is one of the more elegant methods of purifying and separating enantiomers because it can often be done in a single crystallization step. Now, there are a few other methods to separate enantiomers. One method involved would be chiral column chromatography. This is primarily used for quantifying the amount of enantiomer in a mixture. It's not actually used very commonly as a preparative method. So a chiral column contains chiral molecules as part of the stationary phase. And as enantiomers have different interactions with the chiral column, the enantiomers will progress through the column at different rates and exit the column at different retention times. Thus, a mixture of enantiomers can be separated. Very similar logic to our discussion of the stationary phase in the gas chromatography lab. Not quite identical, but a good point to reference. Okay, so that's how we separate enantiomers. It's important to know practically. What we're next going to talk about, what we're next going to focus on, is assigning the stereochemistry for alkenes. So just like our tetrahedral centers, alkenes can possess different shapes depending on the three-dimensional arrangement of our substituents. We can have different alkene stereoisomers. So we have the cis alkene, where the substituents are on the same side of our alkene, and the trans alkene, where our substituents are on opposite sides. Now, this cis and trans definition works nicely when we have relatively simple alkenes. However, when we start to look at molecules with multiple substituents, if there are multiple substituents on the alkene, cis and trans naming conventions sort of fall apart very quickly. Which groups are you referring to? Well, IUPAC has developed a convention of assigning alkenes as Z or E, and that serves to denote the stereochemistry and relative arrangement of our substituents in our alkene. So these rules are going to sound very familiar. First, we rank each group on each side of the alkene separately in order of priority. Next, if the highest priority groups are on the same side of the alkene has a Z configuration. If the highest priority groups are on the opposite side of the alkene has an E configuration. So let's showcase this. So fluorine would be priority 1 compared to this ethyl group. Oxygen would be priority 1. Both of our high priority groups are on the same side of the alkene. So this alkene would be considered a Z alkene. Conversely, if our highest priority groups of fluorine and oxygen are on opposite sides, we would view this alkene as an E alkene. Does that example make sense to everyone? Does that make sense to everyone?
It makes sense, but it almost seems counterintuitive. It seems like the E should go to the one where both are on the same side, and the Z should go to the one where they're on opposite sides. just based on the way the letters look.
Okay. Can I get some confirmation in the chat that everyone's comfortable with this discussion of E and Z alkenes? Does anyone have any questions that I can address? I just noticed the chat is somewhat quiet, so I just want to make sure. Can everyone hear me okay? Is everyone able to see what I'm writing on this OneNote page okay? Okay, perfect. And if you have any questions, don't be shy to ask. What we're going to do next is we're going to apply what we've learned in this section to an example. So I'd like us to assign the configuration for the following alkene. Remember, you look at the left and right-hand side of your molecule on your alkene. You rank the groups in order of increasing priority. If the highest priority groups are on the same side of your alkene, as in if they're on the same side of the alkene, if you split the alkene along the horizontal axis, then it would be considered a Z alkene. If they're on opposite sides, they would be considered an E alkene. So let's take about 2 to 3 minutes to work on this example, and then we'll come together as a group to discuss. I'd like to see in the chat your proposed assignments for the stereochemistry of the following alkene. And if possible, you can share your priority assignments using the annotate tool on our shared class whiteboard. And don't be shy to share any questions or proposed responses that you have in the chat or verbally. I'd like to see some confirmation that everyone is comfortable with this topic and that everyone is able to formulate a perspective and proposed response for these questions, as you'll likely be seeing these questions again on the homework or on future exams. So let's try to get some responses in the chat, or if you have a question, don't be shy to ask a question in the chat or verbally, and I'd be happy to address your questions. At the bare minimum, we should see some proposed responses, some proposed stereochemical assignments for the following structure. So we see in the chat, we have a proposed assignment of E. Do we have some other student perspectives? Does everyone agree with that assessment, disagree with that assessment? What does everyone else think? Try to get a few more responses from other members of the class, and then we'll discuss this example. Or if anyone has a question on this example, don't be shy to type it in the chat or ask it verbally, and I'd be happy to provide feedback. Okay, so let's discuss. So in terms of priority, this one's a bit of a tricky example because if we look at our carbons, so these two carbons are the same, and we have oxygen attached versus carbon attached. So this top group is priority 1. In the second case, we're tracing down our carbons. Remember, our double bond can functionally be treated as if we had an additional bond to carbon. So then, looking at this structure, we see that our bottom alkene is higher priority than our top alkane. So now comparing whether our highest priority groups are on the same or opposite sides. Our highest priority groups are on the opposite sides. Ergo, we would assign this alkene as an E alkene. Does this example make sense to everyone? Is everyone comfortable with this example? Any questions on this example? So this is a good stopping point for this lecture session for today. What we're going to do now is we're going to take a 10-minute break and then resume this lecture and finish up chapter 5 with a few more examples in laboratory. So can I get